We switch back to semiconductor physics and dipolar excitons. So let me just start with this little object again. So we have an electron and a hole. They are separated in space, and by that they have an electric dipole, by which we can play the tricks that if you apply an electric field, we can manipulate it. And then typically what we have heard also within this conference quite often, we start with this Coulomb interface or interaction, by which we can describe it in first order by a hydrogen model, such that we have a Bohr radius which is renormalized by the dielectric function and constant of the material, but also the reduced mass in our materials. And then when we talk about many-body excitations, we have also the thermal de Broglie wavelength, and then we have this interaction as soon as the density is getting high enough, or the distance between two objects is getting high enough. So far so good. There's supposed to be a transition then to many-body physics. We've seen this formula before. And so the outline of this talk is now to show two platforms where these excitons are studied. First of all, 3-5 double quantum walls. In this case, we have gallium arsenide, double quantum walls with an aluminum gallium arsenide barrier. And then, if the time is appropriate, I will also talk about our recent adventures with 2D materials, in particular with molybdenum and tungsten diselenide, where we see similar behavior. The first experiment I would like to share with you is actually on indium gallium arsenide, and there we use the gallium arsenide as a tunneling barrier. So the red ones are the two quantum wells, and what we typically do is we evaporate only 5 nanometers of titanium and gold. It's quasi-transparent, so we can shine a laser light from the top. At the same time, the titanium helps to apply a gate voltage with respect to this silicon-doped backgate. It's this gallium arsenide. And here, typical distances here are, let's say, hundreds to 200s of nanometers, and so you can translate easily the voltage which we apply to the effective electric field. So when I translate this heterostructure then in this band diagram, or the effective band diagram, which is important, so we have the energy versus this z-axis here. And so when we excite the direct excitons, all of our experiments are always resonantly excited, so we excite them at the direct exciton of one of these quantum wells. The electron tunnels to the lower quantum well, equally the hole tunnels to the upper quantum well, by which we have this two wave functions coupled to each other, and then we have the so-called indirect exciton, or it's also sometimes called the dipolar exciton. In this case, the dipole moment is typically half of the quantum well width, and then in this case, the tunneling barrier of 10 nanometers, so we have about 17 nanometers distance of the two electrons and hole wave functions. By that, we have a strong dipole moment. The reduced overlap of the electron and hole gives rise to a rather low oscillator strength, and more importantly for the lab, we have a long lifetime on the order of typically 100 nanoseconds. This is the regime where we operate these samples, such that we can think that these dipoles are thermalized. When you look at the structure, we have indium gallium arsenide. The backgate is gallium arsenide. That gives rise to a peculiarity. We're not starting with dipolar excitons when we apply rather zero gate voltage. We put on titanium on top of the gallium arsenide. There's a Schottky barrier. The height is of roughly, let's say, 0.7 eV. Depends a little bit on the surface, on the passivation, the nanofabrication, what you have done to the sample. So we need to apply a positive gate voltage to have flat band. If we have flat band, the situation is such that the indium gallium arsenide quantum wells have a lower band gap than the backgate, such that we have a doping here from the silicon, and we end up having a 2D electron gas in the lower quantum well. And actually, when we excite now our system, we have excitons on there, plus these 2D electrons. And since we are cross communities interested, I just baptized it 30 minutes ago. It's the excitonic superatom, as Ronan did before. So this is an exciton. It's an indirect exciton, first of all, coupling to the two-dimensional electron gas. So it's not only one electron it's coupling to, but the whole zoo of excitations within the electron. And as we have demonstrated in this publication a couple of years ago, we demonstrated that these indirect excitons can also couple to the integer quantum Hall effect, even the fractional quantum Hall effect of the two-dimensional electron gas. So it's a very complicated optical excitation what we have in there. And you see this is the sort of default where we start with these indium gallium arsenide samples. And then when we apply an even more negative gate voltage, we pull up also this level above the backgate doping, the Fermi level of the backgate, by which we clean up the samples. There's no 2D electron gas anymore, and we baptized it always. It's the kink voltage what we need to apply. And by then we're in this regime here, and then we really have these dipolar excitons. So from the direct exciton we can study this what we call Mahan exciton to the dipolar indirect exciton. Increasing the electric field in the band diagrams gives rise to a steeper slope, and the wave functions are lowered in energy for the electrons and they are increased for the holes, and by that the difference of their recombination energy is reduced. And this is the so-called quantum confined Stark effect. It's linear because in this regime the wave function is basically squeezed to the sides of the quantum wells. So the outer tunneling barriers determine the distance of the two wave functions in first order always. And this is the regime where we operated mostly. So let me guide you into one of these experiments. This is a scanning electron microscope image of one of the top gates. So we look at the top of the heterostructure, and where we have these little pan, which we call the trap gate, and then we have the slide gate and the guard gate. And this is roughly, let's say, 100 to 120 nanometers in between. And when we apply different gate voltages, in particular here negative gate voltage, even more negative gate voltage, and this is slightly positive, we have a potential landscape like this. So we excite at the what we call slide gate here. We generate indirect excitons, as I just demonstrated you, because the electrons tunnel into the lower quantum well. So they sit there, but they feel, they diffuse of course, and then they get trapped into the lower potential here. When you talk about these indirect excitons in terms of Bloch waves, the conduction band for the electrons has a maximum, and for the holes it's a minimum. And here now, in this simplistic sketch, this is then the so-called binding energy, which in gallium arsenide is roughly 3 to 4 milliV, depending a little bit also on the quantum well width, what we have. So what we want to have are trapped indirect excitons in here. And also what we put here on purpose, we dislocated the exciting laser far off, such that basically all the thermalization dynamics occur at the slide gate, and then we look at the trapped, supposedly thermalized dipolar excitons in there. In the beginning, we started this business with the indium gallium arsenide samples because we wanted to excite from the top and detect from the bottom. We wanted to disentangle the excitation and the readout even further. This can be done because the indium gallium arsenide quantum wells have a lower band gap than the gallium arsenide substrate. So for the next 10 slides, I only show you experiments where we detect from the bottom. And so at that time, that was the experiment or the microscope 6 years ago. There was a prototype. You can buy it now at the confocal microscope 3 of Ethercube. That's the prototype of that. They adapted everything. It's basically, we have here our sample. We have the positioned objective from the top, the positioned objective from the bottom. You see, you have to take care a little bit of the lenses because you have different environments, optical environments, when you come from the back. And I can tell you, the chromatic aberration is huge. You have to take care about really what kind of lens you're using. And at that time, we could also apply a magnetic field. It's in a helium-3 insert that has a bath temperature of about 240 millikelvin at that time. Okay, so let's have a look at the experiment. Let's come back to this top view of the scanning electron microscope. We excite here. And now we're just looking at the emission of the direct excitons. The direct excitons, they have a lifetime of, let's say, a couple of hundreds of picoseconds, let's say 1 nanosecond. So the diffusion is 2D, and they spread out only here. So they don't make it very far. They stay in the slide gate. That is good news. That was very promising news for us at that time, because that meant that the excitation energy, the access energy, is mostly located at this spot, several microns away where we are interested in. So this is this position here, and then, of course, at the same time, this is the recombination within the very same quantum well where we excite them. But now we have this tunneling process of the electron to the lower quantum well to form indirect excitons, and they live longer, so they can diffuse further on. Now we look at the emission of the indirect excitons, and they make it also into the trapped. And so it's quite interesting. Here where we excite, everything seems to be diluted. They are moving out of this because they are hotter in this case here. They seem to relax here. And then we're getting this, these excitons trapped here. And you see the trapped exciton cloud, they follow nicely the geometry of our trap. It's very important how you shape basically also this feed line here. Because when you make it too broad, these excitons will basically follow the feed line as well. Okay, and these are basically the parameters which you would like to know if you're working in this field. And then at that time, I mean, this whole concept was driven that we want to go down to single excitons. That was when we started that in 2011 with these indium gallium arsenide samples. So we fabricated traps with a diameter of 11 micrometer. We have an emission of the indirect excitons. We went down to, let's say, almost 2 microns. We have emission of the indirect excitons, but they still behave the same. So let's say here we have 10,000 indirect or dipolar excitons. We're going into 1,000. At 1 micron, we're getting to a few hundreds. At 800 nanometers, it's, let's say, 100 excitons, but still the same. At that time, we wanted to learn about the level structure of these excitons. That was our ansatz. We wanted to know what is the electronic excitation, what can we do with this? To summarize all this extent, it took us 2 years, all these experiments here. Here we explored, let's say, this Mahan exciton, what I mentioned before, this super exciton. And then also we entered this quantum Hall state of this indirect exciton state, discussed some phase transitions. This is summarized here. And then what I show you now is basically for samples 800 nanometers and smaller, where we went into this single exciton regime. And it turned out that we only found it for samples with a diameter of 600 nanometers for the top titanium gate. But this is very peculiar and depends very much on what kind of heterostructure you have. Because when you have a back contact which is very far down there, of course the profile of your top structure does not matter anymore. So you have to balance where you put your back contact, but also where to position your double quantum well. If you put it just to the back contact, we all know Gauss law. So basically the electric field lines, which are important, the perpendicular field lines, they're just uniform, homogeneous. But when you put it very close, you can nicely pattern the landscape of the potential, but then you have the problem that there are differences between the trap gate and the outer gate. So that means you also have horizontal electric fields by which you can separate these charges. So you need to balance it very carefully when you design this experiment. What we saw for these samples, for these with a diameter of 600 nanometers, we still have this linear quantum confined Stark effect. But all of a sudden, for the most negative voltages, I mean, this is also always with respect to the Schottky potential, to the flat band, so to speak. Before it was 0.8 volts, when you remember. So with this, effectively, we apply negative voltage on that. So it's a negative field such that the holes are trapped and the electrons are pinned because of the binding energy. We saw small lines splitting up. And it was quite interesting when we did that. We could also sweep the emission, because we have now, we pump from the top and we measure from the bottom. So we could independently move or scan the lower objective. And we saw that the extension of this emission has something like 2 microns. This is the so-called point spect function when you take into account the geometry where your objective sits, and then we measure 2 microns at 1.38 eV. This is about very close to the diffraction limit, what you get with these objectives, what we have. So the spectra look like this. At very low power, this is 55 picowatts. It was done at Saturday night to Sunday. No one was in the lab. We didn't see anything. But the PhD students were there, disappointed. And then it started. There's one tiny peak, comes up, and now we see the 2 peaks, and this is exactly the laser power where this is measured here. So we start at a lower laser power with a 1 bound quantum confined Stark effect, and then at a higher laser power, all of a sudden we have 2 lines. We increase it, then there's something coming up here, and all of a sudden the whole shape comes to an asymmetric shape. I click it through because it's like this. In a waterfall, you see again that's the first peak, then you see the second peak, and then there's the shoulder coming up, and then you have the emission of the overall photo emission of these indirect excitons. That means, in our interpretation, we have 1 single dipolar exciton, 2, 3, and then we estimated it up to, let's say, 50 to 100, what we got. You also see in this plot nicely the so-called blue shift. It's the texture of the dipole-dipole interaction. And you also see the problem of the field, that this blue shift is not so easy, because, I mean, if you have only 2, I mean, we have this 2-level system in our back, and also the dipole-dipole interaction of 2 objects. That's fine. But when you get more and more, what is the correlation between these excitons? I mean, how can you simplify the blue shift with respect to this bottom line, what you get from 1 exciton? And this was long discussed, about 10 years. What is this effective blue shift correction factor, basically? You have a question? No. Okay. For the first 3 lines, we plot here the photoluminescence, and it goes up. For the first line, sort of linear, then it sort of saturates. As soon as it saturates, the second line comes up in a parabolic fashion. As soon as this saturates, the third line comes up in a sort of power to the third. Yes?
How do you estimate the number of excitons you have? For example, when you are saying 1 exciton, maybe it's in average much smaller than 1.
Very good. Actually, I have it on the second slide. We did some classical estimates. Just what we put into this Hamiltonian, the classical Hamiltonian, I have to say, the dipole-dipole interaction, and then it's we had the transition from 1 exciton to 0, then 2 to 1. These are the ground transitions what we observe with our recombination. But at the same time, we have also excitations within this, as you will see in a second, parabolic shape, because the excitons can move around, or at least the electrons should be delocalized. And you're right, for all these measurements, we have about 10 minutes integration time. we don't know if it's just one or if it's an average one emitting line.
Even when you see two lines, still the question can be much smaller than one.
But, now comes the but. First of all, I mean, I come from 3.5 semiconductors, quantum dots were hip in the 90s. And there's a famous paper also in the Walter Schottky Institute for single quantum dots, fluctuation quantum dots. When the first one should emit linearly, saturating, the second exciton then comes up with a power to the 2 law, saturates, and the third one comes up with a power to the 3 law. And we sort of see that here as well. That's the first indication. The second indication.
Alex, when you talk about 1, 2, 3, you talk about the configuration where you have in the top, emission of 1 exciton or
In average.
2 excitons, and 3. It's not the second, the third, but 2 and 3, right?
No. It's always sequential. That is also what Leonid asked, basically. It's in our understanding how we modeled that. In particular, this energy scale here is that we have a transition from 1 to 0, 2 to 1, or 3 to 2. So because we have always this dipolar blockade in between, if you want.
So you see that's what I of divided density, but when slope changes, this changes one exciton.
That is how we interpret this. Paulo.
When you have the position from 1 to 0,
Yeah.
so your initial state you have 1 exciton, and the final state
Is 0.
but you still see a blue shift of emission.
Of 1.
Yeah.
I mean, I see the blue shift for 2. That's the second one here.
So the first order
So
is what?
this is, look at this, photoluminescent blue shift. So this is, I mean, it's in there, the questions, the answer to your question. So first of all, the transition from 1 to 2 gives me about 2 millieV. But then, when I increase the laser power, the possibility that an average throughout 10 minutes, I have, let's say, an average more 1, but a little bit 2 already. So I have already this blue shift as well in here. It's like an average blue shift of not correctly detected events. And then the third one is then has only a blue shift of 0.5, 0.8 millieV. Yeah.
Let me repeat that. So whenever you see you have the position from 1 to 0, so your initial state you have 1 exciton.
Presumably, yeah.
Yeah, and then your final state is no exciton. So basically you have a well-defined initial state and a well-defined final state. My question is, where does the blue shift come with the intensity? Because even though the intensity is changing, is actually this exciton interacting with something outside? Or
As I said, in 10 minutes, it can be that sometimes there's also a second one in there. And this chance becomes higher and higher the more laser power you apply. And then, let's say after, when this with this curvature changes, it's more likely that you have 2 in average in there.
I guess he's asking about the first rise and up to this bump that you have at half a microwatt or nanowatt.
That you have this shift here.
Yes.
It's also this shift here.
Yes.
That is, in our understanding, we discussed that, I don't know, it took us half a year. It's this presence of a second 2 excitons.
Like in average, it's maybe 0.3.
Yeah.
But still sometimes it even 2 and even 3 excitons.
Yeah.
You think the average is 0.3.
I mean, there's no single shot.
However, this average increases, so probability to get 2 or 3 excitons increases.
It's the difference. I mean, this is not a single shot experiment. We needed to integrate for 10 minutes. And so by that you have a lot of possibilities in there. Okay, but this cascade of energies is very important, or was very important at that time for our understanding, because the way we could model it was the following. So we apply a large negative electric field with respect to the top gate, by which the hole is localized. The electron is bound to that because of the binding energy, by which we modeled it with a parabolic confinement. And with this parabolic confinement, you get these cascades of energies in combination with the dipolar interaction. So you have 2 ingredients, the parabolic confinement plus the dipole-dipole interaction on the single exciton level. And then you get this one. without dipole-dipole interaction, we all know that, we all trained in harmonic oscillator, it's constant, and so forth. So that was quite clear that with this one, it is very much compatible with a parabolic confinement. And what we also had for the discussion, Sasha Govorov from Ohio did this simple theory for us, was basically to get this slide slope out. We said that we have an average and like a Wigner-like arrangement that they could move around. We have some degree of motional freedom in here. Okay, there are two next slides which are related to this image. The first one, when we saw that, we were really happy because we got down to the single exciton, but also we had the smallest emitter which is possible in these systems. So we wanted to measure our point spread function on that. And so this is the setup schematically. And now we can again move the second objective, for example, to the position of the top objective.
DNA?
Excuse me?
The DNA of the objective.
I have to look it up. Sorry, it's typically 0.4, 0.56 or something. At that time. I mean, that's the. Right now, Sebastian is in here. He has rebuilt 2 more microscopes. We're not running this microscope anymore. It's standing at the LMU at the UX. Anyway, so we could measure that point spread function, and the extension is about 1.4 micron, which is okay because we have a diffraction limited spot size from the top to the bottom. If you convolute that, you get a factor square root of 2. This is very much what we see. And at that time, we also started this interferometric measurement following Leonid's work. And basically, for the indium gallium arsenide samples, we did not see any spatial coherence. There are several possible reasons. I mean, we saw temporal coherence. The emission is coherent for 1 picosecond. But the idea of this concept, and we are still following it on our lab right now, is that you have 2 independent objectives on the sample. It's not like a shift interferometry, what Leonid does, or also the mirror interferometry. Our ansatz is basically we want to go to the sample itself. And you have 2 independent point spread functions, which we then can overlap. The proposal still in our lab is, if we have a coherent state all over this place, I mean, presumably the trap, we can separate the 2 foci and see if there's a macroscopic phase. The emission should be also coherent, although the 2 point spread functions on the chip should be separated. This is basically what we do. Yeah. In this case, I mean, 10 millieV, let's say, but now we are also having on the same trap. I know, but
It's 100 Kelvin, so excitons arrive to trap temperature 100 Kelvin.
yeah, we saw that before. But the newest samples have just 1 large trap. So we are in the same spot.
This is also not good because then you have immediate excitation.
Let me.
This is exactly why we work with parabolic.
I know, but don't get into this discussion again. Okay. The second point I would like to make with this diagram, when you look at that, it's a fragile object, right? It's basically stabilized by the positioning of the hole, because we apply an electric field. It's negative, and so the hole is stabilized, and the electron only wants to be there because of the presence of the hole. So it's very likely that the electron, as a quasi-particle in the conduction band or the quantum well, the lower quantum well, which is the quantum well 2, drifts away. And this is what I would like to show you in a other sample in a different heterostructure. So we switched back to gallium arsenide. The newest experiments, the ones which I show you today, are done by samples by Werner Wegscheider, and the running experiments are on heterostructures grown by Michael Manfra and Purdue. So these quantum wells now have a distance or a tunneling barrier of 6 nanometers and a width of 7 nanometers, and we do not have this problem of Mahan excitons, of the super excitonic states. We directly jump into the dipolar excitons. So the samples are similar as before, but now the diameter is large again, and we have the excitation and the detection from the top on the same sample. So with this, we have the trapping potential. And when I translate now this concept, what we learned from the single exciton, to these large traps, we have the following contribution, that we trap the excitons in the middle of the sample, but we also have drift terms for the electrons to the outside. Ronen wrote that 2004, I guess, right? Large review on this, how we should design our samples. So this is well known. But what I would like to point out, you have extra charge carriers, predominantly holes in the traps, and electrons outside. And I would like to make a comment. Please don't start immediately. This also occurs for no traps. Because in 3-5 semiconductors, electrons like to diffuse about 10 times faster at low temperatures than holes do, because of the different masses. So also without the trap drift potential in here, you always have electrons further out than the holes. Actually, this gives rise to the well-known nice rings, what Leonid showed 2 days ago. Because in the middle you have holes, and the outside you have electrons, and just at the counter where both meet, you have these excitons again in the nice luminescence bright spots. Okay, so the point is now, for the next 2 experiments I want to share with you, there are coexisting ensembles of dense, laterally confined indirect excitons, plus a 2-dimensional gas, a 2D HG as we sometimes call it in semiconductor physics, with similar densities. The first experiment I want to show you is where we used or utilized a magnetic field up to 9 Tesla in the Faraday geometry. So that means perpendicular to the plane of the excitons. And this is what we saw at 4.2 Kelvin. So this is just at a certain gate voltage, and for the trap and also for the counter at the gate itself, it's minus 0.4. So we have a certain electric field, and now we ramp up the magnetic field. What we see is the emission gets very broad, several tens of millieV even, and then we have some interesting structures. So let me walk you through how we understand it. The first thing is we looked at the maxima of these emissions, and so the broad peak has this dependence in the magnetic field, and there are tiny peaks up here. They will be important later on. But this allows us to distinguish, let's say, the first regime up to a artificially named magnetic field B star, and the second one B double star. And you see that the emission here explodes. It's much more. So when we saw that, we said, oh, that's very interesting. What is happening here? At high magnetic fields, high electric fields, low temperatures, high magnetic field. And what is going on? So we know that if you have electrons diffusing faster than the holes, at 0 Tesla, you have these extra holes in the center of the trap. But as soon as we apply the magnetic field, we have the cyclotron motion, the Lorentz force. So they go around the corner in classical physics. And there's some way that you can confine these electrons here. What we read out is the excitonic recombination. That means as soon as the electrons in the holes, they meet each other, they can recombine. Again, the electrons are in the lower quantum wall, the holes are in the top quantum wall. So this is a little bit misleading or oversimplifying. When you fit that in first order, you think it's a parabolic change, but the dominating factor or dominating physics or process underlying that is that the electron density increases at the spot where we detect, and by that the hole density decreases because they can recombine such that the indirect exciton density increases. If you translate it to textbook atomic physics, you say, well, it's parabolic, there should be a diamagnetic shift. But if you calculate the mass, the reduced mass in these systems is much too small. So in your head, it's just, let's say, micro-eV, what you can get by this diamagnetic shift. what we find is 10 millieV. So this, the reorganization of the electrons, that's in our understanding the dominant effect. Because once you have these electrons in here, you have dipoles again in there. And as we learned before, the more dipoles you have this blue shift. The blue shift goes up. One can estimate that the exciton density increases by a factor of 2 roughly, already at 1 Tesla. Okay, now comes this intermediate regime between these two artificially named magnetic field, B star and B double star. So in first order, when you look at that, that reminds us of the Landau level scheme what we have. For the experts, you can only measure that once you have a quasi-Fermi level somewhere, presumably the holes, which defines you the recombination line or the energy. So this is consistent that we still have some holes in the system. This is, for example, the first transition from N00, and then that's the second one from N11. However, it's much more complicated. The binding energy of these indirect excitons, they change with the so-called magnetic length, the size a flux has, which is the magnetic field quantized, and then it compares with the distance of the heterostructure of the two quantum wells. So the binding energy changes, and you see this, for example, when you compare the indirect excitons with the ones of the direct excitons, they have also some sort of increase here, but with a different shift. So there's for the direct excitons, you get rid of this one, and in first order you have only this leading term for the binding energy. Then you have this Landau level scheme, what you have up here. But on top, as Leonid showed very nicely, 2001 I think, the effective mass is enhanced. And what I forgot here to list, most dramatically, the lifetime is elongated, it's much longer. And what this means, the density changes. And so by that we sort of argue that we have this increase here. But there's also an increase of emission just at this 7 Tesla roughly here. So what is happening up here? The interpretation what we have is that the indirect energy and density is independent from the trap potential. Let me show you why we think that. So at 0 Tesla, we just measure also for this heterostructure the ordinary, let's say, quantum confined Stark effect, what we have here. At 7 Tesla, at this ominous B double star, this quantum confined Stark effect is not there. We got rid of the electric field on the first view. It's nice. We were totally happy when we saw that. We said, wow, the electric field disappears in the magnetic field. Voodoo. How can that be? So if you compare that, if you have the quantum confined Stark effect shift at 0 Tesla, it nicely follows what you can calculate for these heterostructures. At 7 Tesla, it's flat in first order. And it's even more dramatic when you compare now this energy shift here, what you would expect as a quantum confined Stark effect shift here with respect to what we see at, for example, 0.6 volts, minus 0.6 volts. We can calculate now we put in the energy shift and then calculate the effective density of these excitons. As a function of the magnetic field, it rises. At 7 Tesla, it's maximum. This is this curve here at minus 0.6 volt. It's exactly this blue one here. We find values when you stick it this and put this as 1, as we're supposed to do for this heterostructure. We get densities of about 16 times 10 to 6 per square centimeter. 10 to 10, excuse me. You can all read better than I can. Okay, when you do that now for a voltage of minus 0.4, this difference translates to a lower density, but they all come up to this energy. So we always have basically this maximum density up here. Why is that? In our understanding, we have a trap with such a trap potential. The outside gates, which fix the exciton energy outside, and then we have the trap. Now we have the different terms because of the Landau levels, because of the effective mass change, because of the lifetime change. And now we predominantly fill up the trap. And this is now a shift. It depends on the magnetic field, on the laser power, on the gate voltage. Let me show you the laser power. This ominous dependence comes back to a sort of normal quantum-confined Stark effect when you reduce the laser power to about only 8% of the maximum. Actually, these are two different samples. So we saw it in different samples. I just want to make it clear. But they are very, very similar. When we now increase it up to, let's say, 43%, you see that this quantum-confined Stark effect seems to saturate and then comes down again. And for the maximum power, we just fill up the trap. In the laboratory with Sebastian and Lucas, we called that, hey, it's a completely full trap. Interesting. At 4.2 Kelvin, we can fill up our traps and nothing happens. And it's still, we have problems to understand it completely. I mean, it's clear that this ground state is very complicated. You have all different types on top. That's my understanding. You have puddles. You not only have one extended phase, but maybe localized phases on there. But the more we pump on that, it overspills the trap. So that levels off basically what we can measure. For instance, at this point, at minus 0.6, we have to pump as hard as the maximum power. But at minus 0.2, we only have to pump 40% to fill it up. So it's this interplay between the magnetic field, laser power, and gate voltage. It vanishes at high temperatures. We didn't get down to low temperatures. It relaxes thermally. I mean, with it, yeah. So to summarize that, the energetics seem to be driven by magnetic field-dependent renormalization of the many-body interactions terms, and the energy and the density are renormalized, what we describe with this functionally here, and we have the overflow of the trap. Leonid. In this case, we did not measure that. You're right, but yeah, but this sort of linear increase in magnetic field, and also we see the second emission of this possibly second Landau level. I mean, we have seen similar effects also in a publication in 2011. It was also PIB at that time, on also a different sample. Yeah. The Landau levels are not many body? No. I know. I mean, in principle, yes. But, so what is your point? It's a right, because, I mean, we know the quantum Hall effect, we know, I mean, all constituents what we have in this experiment, and by that, we assume that it's due to many body effect. The dipole-dipole interaction is a two-body effect, right? It's a classical one, but still.
Does your intensity rise correlate with density rise, then time? Do you change the recombination time? Or
as I said before, we did not measure the lifetime in this magnetic field regime, which one has to do, basically. One has to carefully compare basically the lifetime, because I agree that this is presumably the most dominating effect, which you can explain most of it, I guess. And then on top of that, you can discuss the density, because once you have the recombination rate, you can solve the rate equation, let's say. Okay, so the question is now, are the two sub-ensembles, the indirect excitons and the holes, interact with each other also without magnetic field. So I would like to present the following experiment. It's on the same hetero structure, and let's say we have holes on the top quantum well and excitons formed with electrons on the lower quantum well. The densities which we are talking about is about these values here. And what we did now was a light scattering experiment. So we come in with a large aperture, let's say, and not with a large aperture, with a small aperture actually, but at a small angle, large distance, I wanted to say. So in these light scattering experiments, you have to conserve the energy and also the momentum, and the momentum is given by the tilt angle of the sample. And we measure the reflected light or the scattered light by spectrometer. I have to say these experiments were done at the Columbia University together with Aaron Pinchuk at his setups. And so what we see is, as a function of the energy, so this is now this scattered light, it's like a Raman process if you want. In the original data there's a background which dominates everything. If you subtract that, we see small first indications that there are some resonances. And so these resonances are roughly at 0.44 milliV, and the full width is 50 micro V.
Energy shift with respect to the incoming laser.
Yes, it's like a Raman shift, if you want. But we plotted it in milliV because in this community we rather talk about milliV, not wave numbers. So, having in mind that we have holes and excitons, the first answers would be, okay, let's take the Drude dispersion for a plasma, whole plasma with heavy holes in there. Doesn't work at all. But it is well known since the 70s, where the 2D systems were explored for the first time. Once you have such a plasma, it connects, well, the dielectric function connects to the conductive environments as well, in particular to the top gate and also to the holes. So the distance to the top gate is in this case 54 nanometers and to the holes only 12 nanometers. When we put in this renormalized effective dielectric constant, we find an energy of about 0.49 milliV. That's in very good agreement, surprisingly. By that we can explain why at between 0.4 and 0.5 milliV with respect to the incoming laser, we have a small resonance. That was done at high temperatures, but we still see indirect excitons. In this respect, we interpret that as a momentum transfer and to a coherent oscillation of the dipoles, what we have from the excitons, with the extra holes in our system. I'd like to mention when we put in, for example, 54 nanometers, it doesn't fit at all. We get something like 0.8 milliV. If we forget about this term, it doesn't fit at all. I mean, the Drude formula is not correct. Sebastian, 320 nanometers? No. 200 nanometers. So it's even longer. It doesn't fit. The numbers do not fit. No.
200 nanometers, so you have even smaller distance to the top gate.
In this sample, yes.
I see, so your purpose was specifically, because if you make it opposite, then you have excitons, but if you make like you have holes. So what the purpose of the holes?
In this experiment, yes, to demonstrate that. Okay. The question is, we can explain the energy of this oscillation, but why do we see it resonantly at certain excitations? And for that reason, Sebastian performed a photocurrent spectroscopy measurement, and for certain energies, he measured basically this resonance. And where we see the resonance in the resonant inelastic light scattering experiments, we also see the resonance in the photocurrent for the light hole and the conduction band resonance. This is a band structure calculation using X nano. And so we have basically the blue transitions where we excite the system. And then we excite this transfer to the coherent oscillation with the holes. This is our current understanding in here. It's a classical effect, but as I sit here, the PL still shows indirect excitons. Yes? It's a plasma peak, yeah. From that data, they're not in there. I mean, it's just basically we have the indirect excitons in the photo. They are there. We know that, and we also have this resonance when we excite basically the system exactly at one of the transitions to pump the indirect excitons. Yes. Yeah. But you're pumping that at the same time. I mean, you cannot get rid of them. Let's say it like this way. Yeah.
But is that something you can see from this peak to this dispersion? If you just assume a plasma. So in a previous slide.
In principle, it's this formula already. We assume that it's the plasma.
Or without the exciton, or with
It's without the excitons in principle. It's the plasma excitation of the holes in this case.
Can you change the plasma frequency by pumping it harder?
To pumping it harder,
Yeah.
we have to do that. And also the next steps is of course to cool down to lower temperatures. But why I'm showing that here, I think light scattering is a good way for us to get a much better resolution. I mean, this is now at 50 micro eV, and basically what you had on the poster was something like 0.1 millieV, 100 micro eV, so we have a much better resolution on that. Yes, Leonid? At 8.6 times 10 to 4 per over centimeter. It is by the 32 degrees. Yes. In principle, you can, I mean, there's a lot of physics to be done. That is our understanding. Also, I mean, this publication was together with Aaron, but that would be the next step, to change carefully all that. I have to say we were really happy to see something, because we did not know if it works at all.
As far as I remember, Aaron used rating on the top of the sample.
No, not than this. This is really like a sample what we measured before. No. No, Leonid, in principle we can tune that continuously just by rotating the sample in this experiment. And this is a really trap sample as well. So, this is the first part of my talk. Okay. Dear Chairman, can I have 2 minutes to summarize my point? Because I mean, in the abstract of this very nice conference, it said also 2D materials, right?
Okay, we
Yeah.
are not hungry. You can talk about it.
Okay, so you will kill me afterwards, right? I just want to make the main points where I know where the field is of the 2D materials with the intralayer excitons. And so it might be especially interesting for you who are working in the double exciton business. So following this suggestion by Michael Vogler and Leonid, it should be a good system, right? The Bohr radius is quite small. I mean, now the field of 2D materials is discussing the texture of these excitons. So it's a rough estimate, but still. I mean, what I'm saying is there's much more about orbital physics in these excitons of 2D materials, about d orbitals, about different k vectors and so forth. The Rydberg is about 140 millieV, and the TC is supposed to be quite high, but of course it's the first step. If you compare that to the gallium arsenide samples, they are 30 to 40 years behind, right, as far as material science is concerned, I have to say. Okay, and so what we used is a molybdenum diselenide sample on top of a tungsten diselenide sample. We have fabricated in the course of 3 years now 7 working heterostructures. So you have to start from the beginning again. And the main motivation for that is that in principle you have a similar structure as before. In one layer you have electrons, and the other layer you have holes, and that are typically called intra-layer excitons, or as we would call them, small dipolar excitons. After excitation either of the one 2D material or the other one, you can end up by the charge transfer processes always in this black type 2 intra-layer exciton. And we see that. This is one of our experiments here. So it's again this schematic overview where we're heading for. So you see the excitons of the one layer and of the other one. Everything is done at 3 Kelvin in this case. Very important, these emissions are very small compared to the one of the indirect exciton. And there are now a lot of publications these days who are just reporting about that. This one goes down, this one goes up, because the charge transfer itself is very interesting. Because you have a layer of only 1 nanometer, how does it work in the reciprocal space that you get over there? So the question is, where are you smeared out that you can tunnel into the next layer, or do you need imperfections to get over to the other layer? But in principle, it's always the starting point that the emission of the interlayer exciton is dominating. That is the starting point for us to talk about physics.
What's the reason why high proof emission of the lifetime was from
Because most of the charge carriers are sitting, the electrons sit here in the molybdenum diselenide, and the holes here.
I mean, if there's no interlayer tunneling, it should be dark.
They should be dark, yes.
But you see that, so it's lots of
Exactly.
interlayer tunneling.
Exactly. Yeah. Okay. I want to summarize what we know right now. And based upon calculations by Alex Steinhoff and Frank Janke in Bremen, they published in 2014 that the band structure of the quasiparticle changes dramatically as soon as you put in some charge carriers in there, in these 2D materials. For example, these calculations are just without any charge carriers, and then for 3 times 10 to 11 per square centimeters, these are DFT-based calculus, you see that the band structure is renormalized by several hundreds of millieV. And right now in the 2D material community, it's heavily discussed how this quasi-particle renormalization is changed with respect to the excitonic recombination renormalization. What Manfred Bayer told you before on Monday. It's happening here dramatically, with a lot of dramatic impact. This band structure here looks a little bit different to what we have typically in 3-5 semiconductors. So we have an hexagonal reciprocal space. This is the gamma point, K and K dot, and then this is the M point. And then here in the middle, that's the sigma valley. And this sigma valley is most influenced by this charge carrier. Most importantly, the sigma valley can be lower than the K dot, K point. We were the first pointing out that for indirect excitons. Now there are 2 more publications in this direction since March. And what we proposed is that we have interlayer excitons not only close at the K or K prime transition in reciprocal space, but also in this indirect reciprocal transition here. Why we think so? First of all, we had the calculus here. Secondly, we always saw 2 different fluorescence emission. And I want to speed up here because I don't want to walk you through all. I just tell you the main part, which is basically already detected here at 30 Kelvin. At low temperatures, we have this peak here dominating. At high temperatures, you see it up here, the high energy peaks dominates. And so we have a duplet structure. And we carefully performed PL measurements as a function of intensity, temperature, different rotation vectors. You have to take care of all that. And that concluded that it's basically the structure what we have seen before. So let me speed up a little bit. I'm sorry for that now. I wanted to just summarize that, what is important for us. We have long lifetimes in the order of hundreds of nanoseconds for these structures. You can do spin physics and Valley physics with these as well. It's interesting, but it's complicated because now at the indirect reciprocal transition you also have to involve phonons. These excitons are diffusive. They move. That's what we find. It's also interesting for our purposes. And so in principle they're promising, but it's just the start. I mean, there's more texture on that, and it's a proposal. I mean, Leonid, I know that you started that as well in your group, but also to you guys to come with us in this as well, because we have a lot of knowledge in that. Let me summarize. This is what we understand currently for these interlayer excitons. And for the whole talk, I talked about this funky, completely full trap, then about these collective excitations of the holes, and last but not least, I introduced shortly the 2D materials. I would like to thank Sebastian and Lucas, who are with me, but also all my collaborators from Aaron, Michael, Jörg, and Frank for helping us either for the heterostructure, material science, but also for theory. For this, I would like to thank you.